Question 2 is a mass on an air track, collision, and simple harmonic motion. So shown in the figure, a 0.2 kilogram mass is sliding on a horizontal, frictionless air track with a speed of 3 meters per second when it instantaneously hits and 6'2", a 1.3 kilogram mass initially at rest. The 1.3 kilogram mass is connected to one end of a massless spring, which has a constant of 100 newtons per meter. The other end of the spring is fixed. Part A, we're going to determine the following for the 0.2 kilogram mass immediately before impact. So immediately before impact, its momentum is its mass times its velocity, 0.20 kilograms times 3 meters per second gives me 0.6 kilogram meters per second. 1 point for a correct expression for momentum, 1 point for a correct answer. Let's see, I guess this is II. What is its kinetic energy immediately before impact? So we know that kinetic energy is half mv squared. Using the information that we have there, we have 0.9 joules. Right, 1 point for correct expression for K, and 1 point for the correct answer. Right, those are a little plug and chuggy. This is kind of an older problem. I'm guessing just based on the way it's kind of formatted, it seems like some of the older ones, but still good to remember how to do this sort of stuff. So we're going to determine the following for the combined masses immediately after impact. All right, so linear momentum. Well, it's a collision, and it doesn't matter what kind of collision it is. Momentum is conserved, okay? So momentum before the collision is equal to momentum after the collision, and that was 0.6 kilogram meters per second. Okay, because momentum was conserved. So we get a point for a statement of conservation of momentum, and this is good enough, okay? 1 point for that, 1 point for the answer, for sort of regurgitating the answer. Now, in order to find the kinetic energy, which is not conserved in this totally inelastic collision, we need to find the final mass. The final momentum. So we have the mass of the first block times the initial velocity there, and that's equal to our m1 plus m2, and then our v final. So if you substitute the masses and the initial velocity of 3 meters per second, you get a final velocity of 0.4 meters per second. And a quick check shows us that did slow down. So the kinetic energy of the final one here is 1/2, and we've got to add m1 plus m2 times vf squared. That's a squared. So we get 0.12 joules. A quick check tells you that, yes, we did lose kinetic energy, which is what we expect there. So again, I'm repeating myself here. Statement of conservation of momentum, then a statement of the final momentum. You get a point for finding the final velocity, a point for using the sum of the masses, and a point for the correct answer. So all of B nets us 5 points. All right, scrolling down to C. After the collision, the two masses undergo simple harmonic motion about their position at impact. So we're going to find the amplitude of that motion, right? So we can do this a couple of different ways. The amplitude is the maximum stretching or compression of the spring, and at that point, we have the maximum spring potential energy, which is 1/2 kx squared, right? Is our US. At a max, we have US equals 1/2 Ka squared. And that's also the total energy of the system. Okay, we also know that total energy of the system is equal to 1/2 mv squared when v, not f, I want a max there. When a velocity, 1/2 mv max squared. Right. Well, our key here is that we have v max squared. We just solved for it. It's the speed of the two blocks together. It's not going to speed up any faster than that. We have the masses m1 plus m2, and the k is given. It's 100 newtons per meter. So a little algebra gives you an amplitude of 5 centimeters. So the rubric says 1 point for a conservation of energy statement. That's right here. 1 point for using the kinetic energy we determined in part B. Oh yeah, actually we could have just gone right here to the point 12 if we wanted to. And then 1 point for this correct answer. That's part C. Finally, part D asks us to determine the period of harmonic motion. So we know that from our formula sheet, we have 2 pi rad m over k. We have our mass is our combined mass, 1.5 kilograms. Our little k is 100 newtons per meter. And we get a period of 0.77 seconds. So 1 point for a correct expression for T and 1 point for the correct answer. And then there's this extra global point for having 1 correct energy unit and 1 correct momentum unit on our answers in parts A and B and having no incorrect units. All right. So there's an extra point to be had here. All right. You need to show that you know the unit for energy, which is joules, and that you know the energy for, you know the unit for momentum, which is kilogram meters per second. I think that I've really kind of encouraged you to always put the correct units on all of your answers. I would never, ever, ever put an answer in this without a unit. And if you know, for example, a kilogram meter per second squared, that's a Newton, right? But if sometimes that sort of thing escapes you, oh my gosh, I know that's something, or a Newton meter is a joule, or a joule per second is a watt. If you don't remember that a joule per second is a watt, just put joule per second. You'll get credit for that. Unless for some reason the question is simplify your unit or something. I've never seen that. So, don't ever neglect the units because sometimes it won't matter, but more often than not, you can get some points for that. So that is our second one from this problem set.